Now we've talked about issues with getting parallelism in the processor, that is, with the memory and with synchronization and writing parallel programs. Let's talk about what happens inside the pipeline. So if we want to provide even finer grained parallelism, that is smaller and smaller things to do in parallel, now we're going to talk about instruction level parallelism. That is, can we do parallelism where we do multiple instructions at the same time? So the idea of instruction level parallelism is to find independent instructions and execute them in parallel. We already did some of this with the pipeline, where we execute instructions after each other in parallel, but here we're not going to do them after each other. Here we're going to do them at the same time. So here's an example of some code. First cycle we do an add, and then a load, then a subtract, an OR, and a store. So we have 5 instructions here, which will take 5 cycles to execute if we do 1 instruction per cycle. But if we look at these instructions, we can see that most of them are independent. So these 3 instructions could all be executed at the same time if we had enough hardware. And these 2 instructions could be executed at the same time if we had enough hardware. So if we had lots and lots of hardware, we could do this a lot faster. We could run the first instructions all together, so 3 at the same time in the first cycle, and then we could do 2 instructions in the second cycle. So to do this, we need a lot more ALUs, register files, etc. In fact, we need extra ALUs, so we can do an add, a load, and a store at the same time, that is these first 3 instructions, and be able to do a subtraction and an OR at the same time. We need a bunch of extra register ports. So we've got 2 reads here, a read over here, and 2 reads over here, and then we've got 2 writes at the same time. And down here we have a lot of reads and writes at the same time. We need extra control logic for figuring out how to control the ALUs, the memory, detect hazards, and do forwarding. And we need to be able to read multiple instructions for each cycle. So here we need to be able to read 1, 2, 3 instructions at the same time in order to be able to start them at the same time. But the benefit of this is that if we do these instructions in parallel, it now takes us 2 cycles to finish this program instead of 5. So one other thing that's important to look at here, we're doing things out of order. So this store instruction, it came after all the other instructions here, but it's not dependent on any of those instructions. So we can move it up earlier and execute it earlier, and that's what we've done here. We're executing the store at the beginning, even though it's later on in the actual program order. So we've done 2 things to make this run in 2 cycles. We figured out independent instructions and executed them in parallel on more hardware, and we moved the order of the instructions around. So we're executing them out of order. So let's take a look at a simple example here. This is what's known as a static dual issue pipeline. And what we're going to do is we're going to remember that 1/3 of all of our instructions are load and stores. And we're going to figure out, can we do those loads and stores in parallel with other instructions? If we can, 1/3 of the time we're going to get better speed up. So what do we need to do this? Well, we want to run load and store in parallel with the other operations. So we need a second ALU so that we can calculate the load store address. We need more register file ports so we can load out the stuff we need for the load and store address and the data. We need to be able to fetch 2 instructions per cycle. Not just 1, but 2, because now we're going to do a load and store and another instruction. And we need some way to put these instructions together. So here we're going to assume the compiler puts instructions in pairs and we execute them. So this is a dual issue pipeline. So here's the code that we had before, and what's the compiler going to do? Well, the first 2 instructions, that's a load store, down here, number 2, and another instruction, so those can just be put together. But for the next set of instructions, we need to find a regular instruction and a load and store. So we take these 2 and we put them together as a second instruction, and then for a third instruction, well, we don't have a load or store that goes with this third instruction, so we're going to put the OR in there with a no-op, because we couldn't find another load store to put in there. The idea is to execute this on a pipeline where we can do this first instruction and the load and store together throughout the pipeline. This is known as a static multiple issue pipeline. So these instruction pairs are static, they're fixed, and they don't change while the processor executes. So here's the pipeline for that. We've got our program here and we've had to change our pipeline. We put in a second sign extender because we may need 1 for the ALU operation and 1 for the memory operation. We've got a whole bunch more memory ports to the register file so that we can support reading and writing more registers. We've now got 4 outputs from our register file instead of 2. We've got a second ALU for doing the address calculation. And if you look over here at instruction memory, we're now fetching 2 instructions every cycle. So here's our regular data path. We fetch the instruction, we go through the registers, go through some muxes to the ALU, and then we go back and write into the register file. Here's our data path for doing load and store. So we're going to go through the register file, and we're going to go through the sign extension in the ALU to calculate our address and go into the data memory address. And at the same time, we're going to go through the register file to the data to get the data we're going to write. Then we take the output and we put that back into the register file. So we've now made our pipeline more complicated in order to support 2 instructions at once. We've added more register file ports, both for writing we now have 2 ports, and for reading we now have 4. We've added a second instruction fetch over here. We've added a second sign extension so we can sign extend our address. We've added a second ALU for calculating our memory address. And we've added a bunch more forwarding logic and some more paths for moving data around. The result of this is we can now issue both a load store instruction and any other instruction at the same time. So let's take a look at that. Here's our program and here's our pipeline. So our first instructions look like this. We fetch 2 instructions from our instruction memory. The register file is now providing 4 outputs. We have 2 ALUs. One of the instructions is going to access the data memory, and both of them are going to write back to the register file. For the rest of our pipeline, we're going to look like this as well. So if we do this right, we now have a best case where we have an IPC of 2. That is 2 instructions per cycle, or cycles per instruction of a half. It takes us half a cycle on average to do an instruction. So with this design, we can be up to 2 times faster. So a question, why might we not get the full 2 times speed up from a dual issue pipeline? Well, the answer here is all of the above. So as you see, we have a lot more instructions in parallel now. We can have more data hazards. Look at all of the registers that we're reading and writing. We now have almost twice as many, so we're going to have more hazards. We also have extra logic. So this register file now has to be able to read and write more ports. That means it's going to run slower, so it might slow down our clock speed. And as we've seen here, the compiler can't necessarily fill all of the slots. So even though we could have done 6 instructions here, we only did 5 because the compiler couldn't find another load store to put in here. So let's talk about superscalar. So in superscalar, we have dynamic instruction level parallelism. That is, we're going to go and have the processor find the independent instructions. And what we do here is we make things way more complicated. We're going to have the processor look ahead at the next 100 instruction it's going to execute and figure out which ones are independent. And it's going to do this while it's running. So the compiler isn't going to tell it, the processor is going to figure out which ones are independent. We don't even have to do them in order. So once we figured out which ones are dependent, we can do them in whatever order makes the most sense. It's called out-of-order execution. So what do we need to do this? Well, we need a lot of hardware. We need somewhere to store all of the instructions that are waiting. These are called reservation stations, where the instructions can wait until they have an ALU to use. We need something that schedules them. That is something that chooses which instruction should be run next. And then at the end, we need to finish them in order. And the reason we need to finish them in order is that the ISA promises that instructions execute in order. And we need to make sure that it looks that way even if we ran them out of order. So what is the benefit of executing instructions out of order? Why are we doing all this work so we can execute them out of order? Well, the reason is if we execute instructions out of order, we can find more independent instructions and get more instruction level parallelism. This gives us more instructions to run in parallel, which means we can run faster. Of course, it's very complex. So let's take a look at Intel's Haswell processor. This is due later in 2013. And here's a picture of how it looks. So at the top here we have 56 instructions in the decode queue. These are 56 instructions waiting to be decoded. We then have 192 instructions that are being tracked. So the processor is keeping track of 192 instructions that are running in the processor. We have 60 instructions that are ready to execute and are just waiting for a pipeline to use. And as you can see here, we have 8 different pipelines. So 8 parallel pipelines here that are can do different numbers of things. Now to support this whole processor, we have 168 entries in our register file. So this is a little larger than the 32 that we have in MIPS. So what do we have in this Intel processor? Well, this is an out-of-order superscalar processor. This is the most complex type of processor we have to date. It's very complicated, and if you're interested in this and want to learn more, you should take the Advanced Computer Architecture class. The thing to remember for this here is that we've got lots of instructions that are all being processed at the same time, and the processor has to take care of which instructions can be run and how to schedule them on the different hardware. Now, if you look at these different pipelines down here, you can see that not all can do the same thing. So for example, load and store instructions can only be processed through ports 2 or 3. So if we have lots of load and store, they have to go into this part of the pipeline. Similarly, branches can be done on port 6 or port 0. And so if you need to process a branch instruction, you need to wait for one or the other of those ports. So to summarize instruction level parallelism, the idea here is to find independent instructions that we can execute in parallel by adding more hardware. The compiler or the hardware needs to determine which instructions are dependent so we can figure out which ones are okay to do in parallel. This is really complex, really messy, and very important. You can get 2 to 3 times better performance from doing this superscalar and out of order, and 2 to 3 times faster is a lot. However, you're going to pay more than that in power, so 3 to 4 times as much power to get that performance. So this isn't a very good choice for power-efficient processors. And if you remember when we talked about ARM little and big processors at the beginning of the class, we pointed out that the little processor here was in order. And it's in order precisely because out of order costs so much power. Whereas the big processor, which is trying to get performance, is out of order to get better performance. So, a question about ILP. ILP is really complicated, so why do we go through all this work to get it? Well, it makes programs run faster by doing more instructions at the same time. If we can run instructions in parallel, we can take less time to process the instructions and the processor runs faster. But to do this, we have to find independent instructions and have extra hardware to run them in parallel. Here's a question about the static dual issue pipeline. So how often do you expect both pipelines to be full? Well, we expect them both to be full about half the time. So remember, we have a load store instruction about every third instruction, 33% of the time. So we'd expect that every other load store slot will be filled. So for example, if we look at what we have here, we have op1, op2, and a load store. That's a third of the instructions are load store. Then we get op1 in a load store and op2 in a no op. So of course, this doesn't take into account data dependencies and other issues with load stores, which may mean we have actually less than that.